Hello everybody, my name is Jeff Bees and I'm going to talk to you a little bit more about uncertainty, particularly involved with comparing values, using uncertainty, and finding some meaning in those comparisons. This is a continuation from my last video on uncertainty, Uncertainty Part 1. So I'll start out with the question, what is the purpose of uncertainty? Well, the uncertainty is a way of knowing how much variation you can expect about an average. So basically that fluctuation about some target value. And so when you think about averages and fluctuations, you want to think about statistics. And the main visualization you call upon when thinking about statistics is a Gaussian plot, as we can see here, which marks out 1, 2, and 3 standard deviations and what percentage of the distribution is focused between those regions. So plus or minus 1 standard deviation is representing 68.26% of the population. 2 standard deviations represents about 95.46%, while 3 standard deviations is 99.73%. Now, for discussing this, I'm going to relate this to a more tangible topic, and that is tolerances. And so, if you're familiar with machining, tolerances is basically the same thing as uncertainty, but used for machining to dictate how closely you want to match the dimensions given to you for production. So I will actually use a simple example of a screw, where the average value will be the average size or diameter of the screw, and the average will be kind of the ideal situation. And so the ideal situation, as I'm sure you've probably experienced at some point in time, when you get a screw that fits your pre-drilled hole just perfectly, just so that the thread will go into the hole and catch onto that wall, but it will not allow the screw to easily come back out. You can also imagine that there might be a screw that is too small for the hole. And in this case, you would put the screw into the hole and, yeah, sure, it fits in there, but the thread doesn't catch, and in the end it would end up falling out. On the other end of that, we can imagine a screw that is too large. And you try to put this screw into the hole, and it doesn't fit. Now, if we imagine this being represented by that normal distribution, where we have the screw that is too small and the screw that is too large representing the plus or minus 1 standard deviation, as a note, these sizes are exaggerated for the purposes of this thought experiment. Anything outside of that 1 standard deviation would be deemed unacceptable. So in engineering, we use a 95% confidence interval, which you can think of as taking these too large and too small of screws and shifting those out to roughly 2 standard deviations away from the average. I say roughly 2 standard deviations because, as we see below, 2 standard deviations is a little bit higher than 95%. To be precise, 95% would be roughly 1.96 standard deviations instead. And so anything outside of this range would be something that is out of specification. And therefore, roughly 1 out of every 20 of these screws would be out of spec. And you can imagine taking a sample set further out, where we've got even larger or smaller screws than your average screw, and the odds of getting these would be even smaller probability. And so this is kind of the basis of uncertainty. The greater the number of standard deviations away from your average, the less likely it is that it could be made. Now let's think of this in terms of an experiment, where you're comparing 2 values and you're considering one to be your target or maybe theory. And let's put some numbers to this. As a general rule of thumb, if the experimental value that you got is within 2 standard deviations of theory, then that means that you can consider them to be statistically identical, because the natural fluctuation of the phenomena that you're trying to measure not only can reproduce the experimental value that you got, but there is a high likelihood that you will get that kind of measurement if you measure, say, 20 times. Now, in the 2 to 5 standard deviation range, now it's a little bit less likely. It's still possible, but the chance of your experimental value being a representation of the natural phenomena is less. And when we get outside of 5 standard deviations, that means that statistically speaking, the likelihood of there being a match between the phenomena you're measuring and the experiment is almost impossible, because the chances are so minute that you would have to be measuring for an incredibly long time, far longer than any human would reasonably test. Now, these numbers that I'm using are a little bit larger than you might want to think about. In particular, that 5 standard deviations. Once you get out to even 3 standard deviations, that means there's only one defect in every 400 samples. And so moving out to 5, that chance is even smaller. Now, the reason why I'm still going with this is because there's always more uncertainty than you're taking into consideration. Whether that be a draft in the air or fluctuation in your electrical circuits, there's always more than you can account for, and this is kind of taking that into account. Now, as I mentioned before, engineers use a 95% confidence interval, which is, again, roughly 2 standard deviations. So in light of that, we will actually take each of those values I previously mentioned and divide them by 2. So 0 to 1 uncertainty difference is statistically identical. 1 to 2.5 might be the same, whereas outside of 2.5 uncertainty units, then you're in this statistically incompatible region. Now, this comparison may also mean some other things. Your uncertainty might be wrong or incomplete. You could be using an improper procedure, or your theory could be wrong. And yes, that does happen. For instance, if you chose a theoretical equation that maybe didn't have the proper assumptions made, or it was simplifying the situation too much, which is usually the case. So now I'm going to walk through the steps with you on how to actually use the uncertainty. First, you want to determine what you're comparing to. Some possibilities at your disposal are theoretical values, values obtained from some previous experiment, such as what you might get from a literature review, or values obtained within your own experiment. Say you're trying to compare between 2 different scenarios. Next, you want to determine the total uncertainty between those 2 values. And what I mean by that is taking the uncertainty from one of your values and the uncertainty from your theoretical value and combining them using the root sum square method, or RSS. Then you want to take the absolute difference between the 2 values you're comparing and divide it by the combined uncertainty from part 2. Once you have this number, you want to state how much the 2 values deviate from each other, and therefore whether or not they are statistically identical, based on the previous slides where I mentioned the statistical comparison. Note that this statement here is one of the most important statements that you can make about the validity of your experiment, as it tells the reader how much your experiment validates or differs from what is being compared to. Once you've done this, you want to take it a step further and actually compare the relative uncertainties involved in the values and state whether these are particularly accurate or inaccurate values. And then you want to state whether or not your readings confirm your hypothesis or goal. And so an example of this was if part 4 resulted in a statistically identical situation, and your uncertainty was really small, and therefore you had a very accurate system. The conclusion would be that your measurements do confirm your hypothesis. So now let's run through a little example. Here we're given an experimental value of 16.2781 volts and an uncertainty of 4.3421 volts, with a theoretical value of 15.2781 volts and a theoretical uncertainty of 0.1476 volts. First thing you want to do is report these values with proper significant figures. So your experimental value would be 16 plus or minus 4 volts, while your theoretical value would be 15.27 plus or minus 0.15. If you're confused about this, please revisit the last video that I made, which directly discusses how to use proper significant figures. Second, you want to combine the uncertainties of these readings. Note that I'm keeping all the values in the calculation to minimize any rounding error. Then we take the absolute difference between these values and divide by the combined uncertainty calculated in step 2. And for a last check, we would examine the uncertainty with respect to the reading. And here we find that the uncertainty is roughly 27%. So taking these results, we want to put into your report something like this. The experimental value deviates from theory by 0.2 uncertainty units, which means they are statistically identical. However, it is worth noting that the uncertainty within the experiment was very high at 27%, and therefore more testing should be performed with greater attention to increasing the accuracy of the reading. Statements such as this are really powerful and add a lot of credibility to your report. In the end, you always want to ask yourself, does it all make sense? Although it is possible for you to have an uncertainty greater than 25%, it may indicate other things such as a low sample number, or maybe an inadequate piece of equipment or improper testing procedure. Maybe there are incorrect equations being used, or you're improperly accounting for the uncertainty. A quick note is that your total uncertainty should always be greater than or roughly equal to the largest source of uncertainty that you have, and should be on a similar order of magnitude. For example, if we were to combine certainties of 1%, 2%, and 5%, the resulting number should always be larger than 5%, but maybe not that much larger. And again, you always want to ask yourself, is this realistic? I see so many times where people calculate things and get lost in the math. For example, if you were to be calculating something in circuitry and you somehow get a value of 10 to the 27th watts, you're either dealing with something like a Dyson sphere or you're probably not calculating things right. On the other end of it, if you're working on an astronomical scale and you're somehow getting values on the level of micrometers, then you're also outside of the realm of what is realistic for your situation. And that's all I have for you today. I hope that this has been helpful in guiding you in understanding what uncertainty means and how you should use it. I hope you have a wonderful day.